The easier type of statics problem that you'll see are net force problems. In other words, they're going to be problems that involve setting the net force equal to 0. And in some cases, we don't even have to worry about the torque equations. We can just look at the forces, and that's going to be enough to solve the problem. And so here's a classic example that you'll see on a lot of introductory physics tests. So let's say we have a sign that we want to put up. And so we put up the sign and we tie it to the ceiling with some string. It makes some angle theta with one wire. The other wire makes an angle phi. And we just want to find out what are the tensions. So we'll call the left side T1 and the right side T2. So other than just a conceptual problem, this could be useful because for example, if you're an engineer and someone says, well, I need to hang a sign, a very heavy sign for a store, and I need to know how strong the wire needs to be. You want to be able to calculate what the tension in the wire is so that you can make sure that you have a strong enough material, because you don't want it to snap and fall down and clonk somebody on the head. Or at least I hope you don't. So what we'll start doing is we'll just sum up the forces. So what we're really looking at first is we'll just look at the sign. Okay? So the first component we have is due to gravity, we have the mass of the sign times g going down. We have the tension from the sign, pulling it up and to the left from T1 and up and to the right from T2. So now we sum up all the forces on the sign. So we say that F net is equal to, and so we have minus T1 cosine theta and T1 sine theta. We have a positive T2 cosine phi and a T2 sine phi. And then we have a minus mg in the y direction and no x component for gravity. So these are all the forces on the system. So if we were going to write this down in steps, how to solve a problem like this, step 1 would just be sum the forces, which we've done here, and then we set that equal to 0 again, because remember, this is static. This box isn't moving, so the net force on it has to be 0. If there was a net force on it, then it wouldn't be static. It would be dynamic. It would be moving. Okay? So then the second step would be to write a system of equations. Okay, so we have the net force equation, and now we can solve for the x components and the y components separately. So in this case, we can, since there's only two components in the x direction, we see that T1 cosine theta is equal to T2 cosine phi. And then the other equation that we get out of this is we get T1 sine theta plus T2 sine phi is equal to mg. And then step 3 is just to solve for the tensions. Okay, so notice that if we look at our two equations, we have two equations, and we don't know T1 and don't know T2 in the first equation. We don't know T1 and we don't know T2 in the second equation, right? So we have two equations, we have two unknowns, so that's enough to solve the system. So we do that, and so we say that T1 is equal to T2 times cosine phi over cosine theta. And this tells us that, using the second equation now, T2, and then we have a cosine phi, and then a sine theta and a 1 over cosine theta is a tan theta, plus T2 sine phi is equal to mg. So in other words, we see that T2 is equal to mg over, over cosine phi tan theta plus sine phi. And then for T1, so we'll plug in, we'll just multiply T2 times cosine theta, cosine phi over cosine theta, so we have mg cosine phi over cosine theta times cosine phi tan theta plus sine phi. But to illustrate something, I'm going to simplify this a little bit more. If I divide both sides by cosine of phi, okay, so we see that that's going to cancel out this cosine of phi. It's going to give us a cosine of phi here. Well, this is really just tangent phi. And then if I multiply the cosine theta in here, well, this tangent is really sine theta over cosine theta. So if I multiply this in, I cancel out the cosine theta there, I'll get a cosine theta here. So we just have mg divided by sine theta plus tangent of phi cosine of theta. So here's my T1 and here's my T2. So now let's check and make sure our answer makes sense. So the first thing we check is the units. So T2 is a tension, it's a force, so we should have units of force. And we notice that it does because we have mg and then divide it by a number. And then the same thing for T1. But there's something else that we can notice about these. Notice that we have a symmetry. So T2 has a cosine phi times tan theta plus a sine phi in the denominator. T1 has a cosine theta tan phi plus a sine theta in the denominator. So they're basically the same equation, just with different angles. And if we look at the symmetry of the problem, if we kind of draw a line right down the middle, it kind of makes sense that we should have some kind of symmetry between T1 and T2. And indeed, we see that we have that. So a lot of times when you're working these problems, if you work out a little bit more algebra after you get your answer to try and find this hidden symmetry, sometimes that can help let you know if you're on the right track or not. Because if you get an answer that where if you initially look at the problem, it seems that there should be some kind of hidden symmetry underneath, but then when you work out your answer, you don't get that. That can be another check you can use to see whether or not you're doing things right.